Thank you. So broadly, this talk is going to be about a bunch of different programming tools and libraries that you can use as you're studying for Maths 1 and Maths 2. And the examples are drawn from Maths 1 and Maths 2. But broadly, as you'll see, these are certain tools that are applicable beyond just this particular syllabus. They are more generally about graph theory and linear algebra and function approximation and things like that. So why do we even care about programming? Basically, the big idea is that programming is highly synergistic with math. What that means is that being a decent programmer and being a good mathematical problem solver, they often tend to go hand in hand, right? Primarily because programming helps math comprehension. There are some results or some concepts that are better understood if you can write the code for them. And in many cases, you'll see that analytically solving certain problems is tedious, right? You have to do it for your homework and all. But generally, solving things by hand analytically is fairly tedious. It's easier to simply write some program and verify your results, right? And then secondly, the other aspect of looking at the same thing is that math comprehension also helps programming. Sometimes you have to think very hard about what your program is capable of doing, what it should do, what it should not do, what it can or cannot do as well. And math usually helps us define the limits of what a particular program can do. Those edge cases and all, those are typically the result of some fundamental result associated with that particular branch in mathematics. And the third reason is that sometimes we don't have a choice. Some concepts are somewhat counterintuitive. They don't make sense all the time. That's why the only way we can sort of understand them is by writing code. And it's not like that's the only way of understanding those results, but understanding proofs and understanding the rigorous mathematical treatment of a particular concept might be a little difficult. So that is why we use, again, programming as a crutch to be able to understand things better in math. Let's take examples of how this happens. Well, one easy example is polynomials. You'll see that factorizing polynomials or finding their roots and any other sort of analysis on polynomials, it can be very difficult. And in fact, beyond a certain degree, finding the roots and factorizing polynomials is near impossible. It's almost difficult to comment about the roots of a polynomial or where its extrema are or where the roots of its second order derivatives are and so on. But on the other hand, you can plot polynomials very easily. It's almost trivial. If you can write code that actually plots a polynomial, that makes it extremely easy, right? So this is an example of how programming can help math comprehension. You might, by simply looking at a polynomial expression, you might not be able to tell what the roots are unless you apply some very specific factorization algorithm, which, by the way, itself is nearly impossible beyond certain degrees. But if you can plot it, you can very quickly visually see what sort of roots and extrema polynomial has. And once you find one root, then you can, factorize the polynomial and figure out what the other roots are. The other approach where I said that mathematics can also help you define the boundaries of your program. So this is an example from when I was doing PDSA. And there's a lot of graph theory in PDSA. So we had to do a lot of exercises on graph traversal and shortest path algorithms and so on, breadth and depth for searches and many other graph traversal algorithms. So there we needed to come up with random graphs so that we could do exercises on them to see if we actually understood BFS, DFS and things like that properly. But generating a random graph itself is not simply a matter of picking up a particular set of nodes. Let's say you just pick n number of nodes and then you simply randomly decide whether any particular pair of nodes should have an edge between them or not, right? That it's not as simple as that. Fundamentally, it is that. That's how you build a random graph. You pick a set of nodes and you simply go ahead and try to drop edges between two particular nodes randomly. But depending on what you have decided about the connectivity of that graph, that number of edges starts mattering a lot. So there are some graphs that are inviolable. So like if you look at this particular graph over here to the top left, that's an example where the number of nodes, the number of edges is too small compared to the number of nodes, right? And that's why it generates a graph that is not fully connected at all. It's in fact two different graphs, right? So if you really want to generate a set of connected random graphs, then you have to sort of obey the handshake lemma, right? And that tells you whether a particular graph can be at all created or not, right? So this is an example of how some fundamental results in mathematics can help you write your code in a more correct and a more useful way. And then finally, the third example is the Monty Hall problem. The result is so counterintuitive, it simply doesn't make sense. And the only way that you can convince yourself that it is actually right is by running a bunch of Monte Carlo simulations. In fact, I think there's a bug in the code. I clearly made some mistakes in calculation. The probability of you winning a prize after switching a door is 2 out of 3, 0.66. It's not zero point 0.5 as this graph seems to suggest. So what you do is you run a bunch of experiments, and in half of those experiments, you make the player switch the door, and in half of them, you make the player stick with the particular choice. And you see what the probability of winning the prize is over the course of thousands of experiments. So this is called a Monte Carlo simulation. You might have done activities like this during the Stats 1 and Stats 2 courses. So this is the third category of problems where where programming becomes complementary to the mathematical problem that you're trying to solve. The result is so ridiculous that the only way you can convince yourself that it's right is by running simulations, right? At least one thing has to be correct. Like either your analysis about the problem has to convince you that something is right, or you write code simulations and figure out and conclude something which is unambiguously true from the results of the simulation. So let's take a quick look at the syllabus that we have in Math 1 and 2. You'll see that in Math 1, there is about 8 weeks of functions and single variable calculus, followed by 2 or so weeks of graph theory. And then in Maths 2, there is a lot of linear algebra and multivariate calculus. So now let's come to the sort of tools and libraries that you are going to need, or which I believe you will find most useful when dealing with this sort of these sort of mathematical topics computationally. The first and foremost, the biggest, most important library that you're probably not just for math, but for the entire 3 years of this course is NumPy, stands for Numerical Python. This is the sort of thing that lets you do MATLAB kind of things in Python. Python, as you know, by itself doesn't have a lot of numerically intensive functionality, and NumPy brings that to the table. Then there is a library called Network X, which lets you create and visualize graphs, also manipulate different graphs using certain properties of those graphs. All those properties which you're going to study in Maths 1, Maths 2, maybe in computational thinking as well, and certainly a lot in PDS. Right? And then finally, another very useful library from a homework perspective, this is SymPy, stands for Symbolic Python. This is something that you can use pretty much every day as an alternative to pen and paper calculations, right? And let's go through them one by one. So NumPy basically is something that lets us do MATLAB kind of stuff in Python. So anybody who's familiar with MATLAB knows that you can't straight away pick the kind of MATLAB code, array-oriented code that you write line by line and translate it into Python. NumPy is what lets you do that. It essentially adds arrays, vectors, and matrices in Python. You can do a lot of linear algebra in NumPy. Pretty much all linear algebra that you are likely to need is there in NumPy. It has large libraries on Fourier transforms, and it has a bunch of basic statistics also. And then finally, there's also Network X. So we can convert dictionaries and arrays into graphs. So if you remember, there are things like adjacency lists and adjacency matrices, which are essentially either lists of lists or dictionaries in Python. And you can simply use literally take those dictionaries, put them into a Network X class, and that creates the corresponding graph. You can do graph traversal. You can study different properties of graphs, and of course, one of the most important contributions of this library also is that it helps you do visualization of graphs very quickly. If you wanted to simply visualize graphs, then in Matplotlib or something, if you wanted to do it, you would have to go draw each node separately, and then depending on whether there's an edge between them, draw that particular edge. But this is something that lets you do all of that in a much more flexible way. And of course, the kind of graphs that we have studied so far are somewhat simple in the sense that there can be a weighted edge, there can be an unweighted edge, or there can be a directed or an undirected edge. That's about it. But in real life scenarios, you'll also encounter things that are as complicated as graph databases. where the edge and the nodes can be arbitrary objects. They don't have to be letters or numbers or simply, scalar weights associated with a particular edge. They can be absolutely any object, because typically we use graphs to store data, and that data can come in any shape and form. So typically, this is the kind of problem that Network X solves. And finally, there is symbolic Python. Now, you see, it's not possible to write x plus x equal to 2x in Python, because Python will start complaining, what is x? You haven't told me what the value of x is, so I can't parse this particular expression. But Sympa is something that lets you introduce symbolic variables into your code. And then you can do a lot of things based on just those variables. As an example, you'll see that this is a function. It's a scalar valued function of two variables. So it's a bivariate function. And this is called a Mexican hat wavelet or a recur wavelet, right? And in some of the later parts in mathematics too, if you remember, we had a bunch of content on how to draw tangent surfaces to a function at a particular time, at a particular point in the domain of that function, in a particular direction, right? So this essentially is a bunch of SymPy code which actually simply figures out that particular tangent surface. And if you remember, the expression that you get for those tangent surfaces is parametric. It's not numerical. So for example, if there is an f of x and y, and you try at point x0, y0, what's the tangent surface which points in a particular direction, the result is often a function of some parameter, right? We call it t, or you could pick any other parameter. And this is the expression of the wavelet that you see here. And when you run this function solve, it's basically solving for the tangent to the function f at a point 6,0 towards the direction 10, or towards the positive x-axis, right? And you see that you get the result isn't a number. It's not even a vector. It's actually a set of three functions, each of which is parametric. So it's actually an expression of t. It's a function of t. And you see that t doesn't have to have a value. Now, typically, this is something that's almost impossible in Python, because it can't produce functions of other parameters. It can only produce numbers. It can produce scalars or vectors, but it can't produce symbolic output. So you see that f here is kept symbolic. You just declare that x, y, and t are symbols. You can simplify expressions based on that, and you can do a lot of arithmetic based on that. You can differentiate those functions, find the roots of the differentials. You can also do row reduction for matrices, and the matrices themselves can be symbolic. They don't necessarily have to be real valued matrices as such. I'm sorry, real valued matrices, they have to be, but the elements of those matrices themselves can be variables, right? So this is again a very useful library that I would highly encourage you to check out. The other thing that I'd like to leave you with is that symbolic computation, or CAS as it is called, computational algebra systems, they are very critical for deep learning also. Typically, deep neural networks, they represent functions that can very quickly get very complex. So if it's a straightforward neural network, then you know that the output is of a certain form. But deep neural networks can get really, really ridiculously complex, and the output that you get, or the loss functions that you apply to them, they can also get really complex. And that is why solving them by hand, or differentiating the loss function for a particular neural network and expressing that loss as a function of the different inputs, x, which is your input data, and the parameters of the model, the weights and the biases, that's not trivial at all. So no closed form solution may also exist. So that is why the only way that you can find the gradient of the loss function, because you need to ultimately do what is known as gradient descent, you have to resort to symbolic manipulations for that. But then again, doing that on paper is difficult, because these are networks, and you'll see nowadays that there are neural networks coming up with billions of parameters, not just one. So you essentially have to have a billion gradient descent equations, each of which is solving for one particular optimal value of one particular parameter, and so on, right? So that is where this concept of autograd comes from, autograd or automatic differentiation, or automatic gradient computations, essentially. What they do is the autograd systems, they build the gradient expressions as you are defining them. So here is an example. Let's say v is simply the product of x and y, and then you take the log of v, and that produces some value called w. As you're doing the forward pass, at each point an operation happens, it's there itself. It keeps the gradients with respect to x and y, and it stores a little copy of that gradient there. So by the time you reach to the end of the network and you have to backpropagate to minimize losses and so on, the gradient is already there with you. So the gradient itself is incrementally, symbolically built as the network is defined, right? So this is again one area where the symbolic computation matters. In fact, libraries like TensorFlow and PyTorch, this is sort of the backbone of that. So this and the fact that they run on GPU is what actually makes those libraries really powerful, right? Finally, I'd like to leave you with a little bit of caution. Use programming only to learn things. Remember that don't get overly attached to it, because you will not have access to Python during quizzes. But other than that, do feel free to have fun. Thanks a lot. If there are any questions, happy to take them now. Yes, we have trillion parameter networks now. True. Finding math very difficult. I'm a working professional and I studied formal math long time back. Can you please share your advice on how to go about learning math 2 and stat 2? Balasubramanian, please reach out to me. I'd be happy to share whatever. There's a bunch of content lying around in many places. I'd be happy to share it with you. All right. So if there are no more questions, thanks a lot.
Thanks, brother.